Train Safety Pilot Vehicle, a proposal for collision prevention. The problem. Train collisions remain among the most serious accidents in modern transport. When a train traveling at full speed strikes an obstacle, the consequences are frequently catastrophic, resulting in loss of life, significant economic damage, and prolonged disruption to rail networks while tracks are repaired. The fundamental challenge is physics. Trains combine high mass with high speed, resulting in stopping distances that can extend to several kilometers. If an obstacle appears on the track, whether a vehicle, fallen tree, or another train, the locomotive often cannot stop in time. Additionally, track defects such as heat-induced buckling or ground erosion can cause derailments with equally severe outcomes. Current safety systems, while valuable, cannot fully address these risks. A new approach is needed. The proposed solution. The solution is a pilot vehicle, a self-propelled cart approximately the size of a passenger car that travels ahead of the train to verify that the track is safe. Core mechanism. When the train is stationary, the pilot vehicle remains coupled to the locomotive. Once the train begins moving, the vehicle detaches and travels ahead at a calibrated distance. This distance increases proportionally with speed. The faster the train travels, the greater the gap between the pilot vehicle and the locomotive. The pilot vehicle maintains its position through continuous speed adjustment, using double wireless communication to coordinate with the locomotive's control system. If an obstacle is detected, the vehicle transmits an immediate warning signal, giving the train sufficient distance to brake safely. Why this works? Because the pilot vehicle is far lighter than a train, it has a much shorter stopping distance. In most scenarios, both the vehicle and the train can stop before any collision occurs. Even if the pilot vehicle does strike an obstacle, the impact is far less severe than a full train collision would be. Additional capabilities. Beyond basic obstacle detection, the pilot vehicle could be equipped with rail condition sensors to identify track defects, such as heat buckling or erosion, crossing verification systems to confirm that barriers and warning signals are functioning at level crossings, thermal imaging to detect people or animals near the tracks, snowplow attachments on larger vehicle variants for winter operations. The vehicle's passage also serves as an advance warning to anyone near unguarded crossings that a train is approaching. Limitations. No system eliminates all risk. The primary limitation is the gap between the pilot vehicle and the train. In rare cases, an obstacle, such as a falling tree or a vehicle, could enter the track after the pilot vehicle has passed, but before the train arrives. In such scenarios, a collision would still occur. Cost-benefit analysis. The pilot vehicle would cost a fraction of the locomotive it protects. Manufacturing and operating costs are modest compared to the expenses associated with major train accidents, which include emergency response and investigation, track repair and service disruption, legal liability and compensation, loss of public confidence in rail transport. More importantly, the system addresses the human cost. If this approach could prevent even a significant portion of collision-related fatalities, the investment would be justified on ethical grounds alone. Conclusion. As high-speed rail networks expand globally, the consequences of collisions become ever more serious. The pilot vehicle concept offers a practical, cost-effective layer of protection using established technologies, wireless communication, sensor systems, and autonomous vehicle control. The core principle is simple. Verify the track is safe before the train arrives, not after it is too late to stop. Please share the video. Distribute it to manufacturers of train safety equipment and ask them to give me reasonable financial compensation for the idea. Anders Ullberg, Sundsvall, Sweden.